Okay, settle in, everyone. Today, we're going to dive deep into something pretty fundamental, the invisible superhighways inside your computer.
Yeah, we're talking about the tech behind PCI Express.
Exactly, that connection, that lets your really power-hungry components talk to each other super fast.
It's not just abstract tech, is it? It's actually the bottleneck for a lot of modern computing.
Right, things like AI training, machine learning.
HPC simulations, huge data transfers in data centers, even high-end gaming, actually. They all need to shuttle these massive amounts of data between, say, the processor, memory, accelerators.
Then they need it fast, like right now.
Right now, no waiting.
And PCIe, it's been the champ for this internal data stuff for, over 20 years now?
Easily. And what's kind of wild is how it keeps doubling its bandwidth, generation after generation.
While staying compatible. That always amazes me. It feels like this constant race against, physics, pushing the limits every few years.
Absolutely. And, that race means big changes have to happen, right down at the fundamental level.
You mean how the actual electrical signals, the ones representing the bits, get sent down those little copper traces?
Precisely. The physical layer stuff.
Which is exactly what we're getting into today, thanks to the sources you sent over. So for decades, PCIe used this method called NRZ, non-return to zero.
The standard workhorse.
But then, starting with PCIe 6.0, there was this huge pivot, a fundamental shift to something else entirely. PAM4.
PAM4. Four-level pulse amplitude modulation. Quite a mouthful.
It is. So our mission for this deep dive, using your sources, is to figure out why. Why was this dramatic shift needed?
And how does PM4 manage to double the bandwidth? What are the trade-offs? Because there are always trade-offs.
Oh, always. And crucially, what kind of complex engineering had to happen to make PM4 actually reliable enough for something as critical as PCIe?
All right, let's dig in.
Okay. You mentioned the demand is just relentless. Can you give us a bit more context? Why did these interconnect speeds suddenly become such a critical bottleneck?
Well, think about GPUs today. Graphics processors, right? Their raw compute power is just exploding exponentially.
They can chew through data like crazy.
Incredibly fast.
Yeah.
But they need a constant fire hose of data to actually do that chewing. If the connection back to main memory or storage can't keep up,
the GPU just sits there, twiddling its thumbs.
Pretty much. It's idle, waiting for data. Your sources really highlight this, especially with AI and ML training needing just gargantuan data sets fed to the GPUs constantly.
Right. It doesn't matter how fast your engine is if the fuel line's too narrow.
Exactly. And PCIe, from its early days at 2.5 gigatransfers per second all the way up to 32 GTs with PCIe 5.0.
It was basically trying to widen that fuel line every generation.
Using the same fundamental NRZ technology, yeah. Just pushing it harder and harder.
So let's talk about that old tech then. NRZ, it was the foundation for so long.
Yeah.
How does it actually work, fundamentally?
NRZ is, it's the classic digital signaling you probably learned first. You use two distinct voltage levels, one high, one low.
High for one, low for zero, or vice versa.
Typically, yeah. The signal switches between these levels to represent the bits. And the key part of non-return to zero is that the signal stays at that level for the whole bit time. It doesn't necessarily drop back to zero between, say, two ones in a row.
Just simple on-off, high-low states.
Exactly. And for NRZ, one bit of information gets transmitted per symbol within what we call a unit interval, or UI.
Okay, 1 bit per symbol time.
Which means the symbol rate, that's the baud rate, how many times per second the signal could change levels, is exactly the same as the bit rate.
So if you want 32 gigabits per second,
you need to signal at 32 gigasymbols per second, or 32 gigabaud. They're the same for NRZ.
Seems straightforward enough. What made it the go-to choice for so many years?
Well, its simplicity was a huge advantage, especially early on. The transmitter and receiver circuits were less complex.
Cheaper to build.
Generally, yes, and often lower power, at least compared to more complex schemes at similar speeds back then. But crucially, at those lower speeds, where the signal didn't get mangled too badly going through the channel, you had a really big voltage difference between the 0 and the 1. If you look at the signal on a scope, you get this nice, wide-open eye diagram.
The eye diagram. Lots of margin.
Exactly. A big vertical opening means a good signal-to-noise ratio, SNR. It makes it really robust against noise interference.
Okay. Simple, efficient, tough in its comfort zone,
Yeah.
but obviously it hit a limit. What finally stopped NRZ in its tracks for PCIe?
Yeah, this is where physics really bites you. The problem is channel loss, specifically how much worse it gets at higher frequencies over copper.
Right. Copper traces on a motherboard aren't perfect wires.
Not even close. To double the data rate with NRZ, you have to double the symbol rate, right?
Bit rate equals symbol rate.
And doubling the symbol rate means doubling the Nyquist frequency. That's half the symbol rate, and it kind of represents the highest frequency components you absolutely need to transmit the signal faithfully.
All right.
And copper traces, cables, connectors, they all act like filters. They increasingly attenuate or weaken those high frequencies.
So the faster you try to signal with NRZ, the more the signal gets squashed.
Massively squashed. Your sources have a great example. A channel might lose, say, 33 decibels, 33 dB at 14 gigahertz, which is close to the 16 gigahertz Nyquist for PCIe 5.0. Manageable with effort.
Okay.
But trying to hit 64 gigatransfers per second with NRZ, that would need a 32 gigahertz Nyquist frequency.
Double the frequency.
And at 32 gigahertz, the loss over that exact same channel could easily jump to something like 60, maybe even 62 dB.
62 dB. Wait, how much signal is actually left after that kind of loss? Is there anything left?
Barely. That's losing well over 99.999% of your signal power. It's incredibly weak. And trying to recover a clean digital signal from that tiny remnant while also fighting off other horrible effects like intersymbol interference or ISI.
That's where the bits smear into each other.
Yeah, because the channel disperses the signal energy. And with NRZ at these speeds, the unit interval, the time per bit, is also getting really short, making it even more susceptible to that smearing. Equalization helps, but compensating for 62 gigabits of loss with NRZ just becomes, well, impractical, extremely difficult, power-hungry, expensive.
So NRZ basically ran out of road around 56 gigabits per second over normal copper distances.
That seems to be the practical limit, yeah. Pushing further needed exotic, expensive board materials or super short connections, not feasible for mainstream motherboards or servers.
So the very simplicity of NRZ, its strength at lower speeds, became its weakness. It just wasn't built to handle those extreme high-frequency problems.
Exactly. Trying to slap enough compensation onto NRZ to make it work at 64 GTs was just not a viable path forward. That's what your sources mean by hitting the signal integrity wall.
Okay. And that wall is what forced the big leap. The paradigm shift to PAM4 for PCIe 6.0. So how does PAM4 get around this fundamental NRZ problem?
Well, the core idea is different. Instead of just 2 voltage levels, PAM4 uses 4 distinct amplitude levels.
The rare levels.
And these 4 levels can represent all the combinations of 2 bits, 0, 0, 0, 1, 10, and 11.
Ah, okay. So each signal level now carries 2 bits of information instead of just 1.
Precisely. That's the key. For every symbol, every time the signal level settles, you're transmitting 2 bits.
So for given symbol rate, you're sending twice the data.
Exactly. You've got it. So let's take PCIe 6.0. Aiming for 64 gigatransfers per second, and that's 64 gigabits per second effectively, with PAM4 carrying 2 bits per symbol.
It only needs to run at 32 gigasymbols per second, 32 gigabaud.
Yeah, got it. 32 gigabaud.
Wait a second. 32 gigabaud? The Nyquist frequency is half of that, so 16 gigahertz. But PCIe 5.0 running at 32 GTs using NRZ also had a Nyquist frequency of 16 gigahertz. 32 gigabaud NRC2 equals 16 gigahertz Nyquist.
Exactly. And that is the absolute killer advantage of PAM4 in this context. That's the real carrot, as one of your sources put it.
Wow.
By switching to PAM4, PCIe 6.0 doubles the bitrate to 64 GTs, but it achieves this at the exact same 16 gigahertz Nyquist frequency as the previous 32 GTs NRZ generation.
So the channel loss it experiences.
Yeah.
It's basically the same loss that PCIe 5.0 designers already had to deal with.
Broadly speaking, yes. Since channel loss is so strongly dependent on frequency, operating at 16 gigahertz means the fundamental signal attenuation challenge is similar, even though you're pushing twice the data through.
That's huge. It means you avoid that terrifying 62 dB loss cliff you'd hit with 64 GT's NRZ. You can potentially use similar or maybe incrementally better board materials and connectors as PCIe 5.0.
It's the core reason why 64 GTs became feasible over standard copper interconnects. It allowed the industry to leverage all the experience and infrastructure knowledge gained from making 16 gigahertz channels work for Gen 5.
Okay, PAM4 sounds almost magical then. Double the data, same frequency challenge. But you don't get something for nothing, right? Packing 4 levels into the same voltage swing as 2, there have to be downsides.
Oh, absolutely. Big ones. You nailed the main issue right away. 4 levels crammed into the same voltage range means the spacing between adjacent levels is much smaller.
So instead of one big eye diagram like NRZ, you get 3 smaller eyes stacked on top of each other.
Exactly, 3 eyes. And each one is roughly only 1/3 the vertical height of the single NRZ eye.
Which means much, much less room for error, less tolerance for noise.
Precisely. That translates directly into a significantly lower signal-to-noise ratio, SNR. Your sources put numbers on it. Theoretically, it's about a 9.5 dB hit to SNR just from the modulation change. In practice, with other factors, it's often closer to an 11 dB penalty.
11 decibels worse. SNR. That makes the signal way more vulnerable, doesn't it? To noise, to jitter, to any kind of interference.
Dramatically more vulnerable. And that poor SNR leads directly to the next big problem, a much higher raw bit error rate, or BER.
More errors coming straight off the wire before you even try to clean things up.
Orders of magnitude more. PCIe 6.0 actually specifies something called FBER, first bit error rate, because PAM4 errors, especially with the equalization used, often occur in bursts. The target FBER is around 10 error.
1 in a million.
Yeah. Now compare that to the 10 error target 1 in a trillion for previous NRZ generations.
Wow, that's a million times more raw errors expected with PAM4.
That's the scale of the difference, yes. It's fundamentally a much dirtier signal at the physical layer.
Okay, so how on earth do you build a reliable data link, like PCIe needs to be, on top of something that seems inherently so error-prone?
That's the crux of the PAM4 strategy. You basically accept that high raw error rate is unavoidable, and then you throw sophisticated digital signal processing, DSP, and mandatory error correction at the problem to recover the data reliably despite the errors.
Ah, so the complexity moves into the chips.
Big time. The transceivers, the PHYs, become vastly more complex. You need fancy DACs, digital to analog converters on the transmit side to create those 4 precise levels. On the receive side, you need complex analog front ends, maybe high-speed ADCs, analog digital converters, or multiple comparators, slicers, working together to figure out which of the 4 levels was actually received.
And getting the timing right, the clock and data recovery, CDR, must be a nightmare with 3 decision thresholds instead of just 1.
Much, much harder. The PAM4 CDR needs to track timing across multiple possible transitions, make decisions based on 3 voltage thresholds, deal with eyes that might not be perfectly symmetrical.
Yeah.
It often requires very intelligent algorithms, sometimes selecting specific edges that are cleaner for timing extraction.
And because of that million times worse raw error rate, error correction isn't just a nice to have anymore.
Absolutely mandatory. FEC, forward error correction, is baked right into the PCIe 6.0 standard at the physical layer. It's not optional for PAM4 speeds.
And all this complexity, more complex silicon, heavy DSP, that usually means more power, right?
Generally, yes. Compared to a simpler NRZ PHY at a lower speed, the PAM4 PHY, with all its DSP for equalization and the FEC logic, does tend to consume more power. However, it's a trade-off, remember.
Right. The alternative wasn't pretty either.
Trying to make NRZ work at 64 GTs would have required incredibly power-hungry analog circuits just to fight that massive 62 dB channel loss. Plus, PCIe 6.0 introduced new low-power states like L0P to help manage power when the link isn't fully active. So while the PAM4 chip itself might be thirstier, the overall system power compared to a hypothetical 64 GT's NRZ solution might actually be competitive, or even better in some scenarios.
So the fundamental deal with PAM4 is accept a noisy, error-filled signal off the wire, but then use brute force digital processing and clever error correction in silicon to fix it.
That's a good way to put it. You shift the burden. Instead of demanding near-perfect analog performance from the channel at frequencies where it's prohibitively expensive or impossible, you shift the complexity to the digital domain to the silicon.
Which benefits from Moore's law, getting cheaper and more power efficient over time.
Exactly. It's a strategic bet on the scaling advantages of digital CMOS technology versus the increasingly difficult physics of analog channels at very high frequencies.
Okay, let's just quickly nail down the key differences again, like a quick mental comparison chart.
Sure. NRZ, 1 bit per symbol, 2 levels. Nyquist frequency equals the bit rate. High SNR, low raw BER, aiming for 10.0. Simpler silicon, FEC usually not needed at the PHY level.
Got it. And PAM4?
PAM4, 2 bits per symbol, 4 levels. Nyquist frequency is half the bit rate, or same as the civil rate. Low SNR, high raw BER, targeting 10 AO FBER. Much more complex silicon mandatory FEC required.
And the big reason PCIe made the switch was that PAM4 let them hit 64 GTs while keeping that Nyquist frequency down at 16 gigahertz.
Matching the frequency challenge of the previous 32 GTs generation instead of doubling it to an unmanageable 32 gigahertz like NRZ would have required.
Which let them reuse channel knowledge and avoid crazy expensive system costs.
Pretty much. It was the enabling technology for continuing the PCIe speed roadmap using channels that were, let's say, within the realm of feasibility.
Can we quickly trace how PCIe signaling got here? What came before?
Sure, PCIe 1.0 and 2.0 started with NRZ, but they also used something called 8B10B encoding.
Ah, yeah, I remember that. Added quite a bit of overhead, didn't it?
It did, 20% overhead, but it was crucial back then for things like ensuring enough signal transitions for clock recovery and keeping the signal DC balanced, necessary evils at the time.
Then for Gen 3 and 4, they got smarter, still using NRZ though.
Right. They moved to a 128B 130B encoding, much more efficient, dropped the overhead to only about 1.5%. This was a key step getting more useful data through without cranking up the raw signaling rate quite as much. It helped delay hitting that NRZ frequency wall.
And PCIe 5.0 pushed NRZ right to that edge.
Pretty much. 32 GT's NRZ with a 128B 130B encoding. That meant operating at the 16 gigahertz Nyquist frequency. Your sources describe this as really pushing NRZ to its absolute practical limit on typical server channels. It was considered the most challenging NRZ channel implemented at scale.
Which brings us right back to PCIe 6.0. Why was PAM4 really the only practical choice to get to 64 GTs then?
Because, as we keep saying, 64 GTs with NRZ demands that 32 gigahertz Nyquist. And the channel loss, the signal degradation at 32 gigahertz over standard copper pathways, was just deemed insurmountable for a reliable, cost-effective, mass-market interconnect like PCIe.
No amount of equalization could fix that cheaply.
Not with NRZ's structure. PAM4 was the only mature modulation scheme available that offered a way out. It achieved the 64 GT's target by using that lower symbol rate, 32 gigabaud, which kept the critical Nyquist frequency down at the already challenging but manageable 16 gigahertz level.
So it wasn't just about hitting the speed number. It was about hitting it without needing completely redesigned, ultra-expensive motherboards and systems. PAM4 at 16 gigahertz Nyquist was the key.
Exactly. It allowed them to maintain similar channel reach expectations as Gen 5 and leverage the huge amount of industry experience built up around designing and validating 16 gigahertz channels. Plus, PAM4 wasn't entirely new. It had been deployed successfully in other high-speed standards, like Ethernet.
De-risked it a bit for PCIe.
Reduce the adoption risk, yeah. And importantly, PCIe has always had a laser focus on low latency. That requirement heavily influenced how PAM4 was implemented in PCIe 6.0, particularly the error correction approach.
Okay, let's really get into the nitty-gritty then. How did PCIe 6.0 actually make PAM4 work, given all those challenges we talked about? What specifically changed in the PHY architecture?
Well, the complexity just exploded inside the chip. On the transmit side, you can't just flip a switch between two voltages. You need a more sophisticated D-Day or something equivalent to generate 4 distinct, stable, well-defined voltage levels.
And receiving that must be tricky too.
Very. The receiver needs a sophisticated analog front end. And then, instead of one simple decision circuit, it needs multiple high-speed comparators, often called slicers, or maybe a flash ADC, working in concert to make 3 simultaneous decisions. Is the signal below level 1, between 1 and 2, between 2 and 3, or above 3?
3 decisions at once to decode the 4 levels. Wow. And managing the timing, the CDR, we touched on that much harder.
Significantly harder, yeah. The CDR logic has to potentially track timing information from transitions between any adjacent levels, 0, 1, 1, 2, 2, 3, and maybe even non-adjacent ones. It needs to make accurate timing decisions relative to 3 different voltage thresholds, often dealing with eyes that aren't perfectly symmetrical in time or voltage. Modern PAM4 CDRs use complex algorithms, sometimes adaptively choosing which signal edges provide the most reliable timing lock.
And we mentioned FEC forward error correction is baked in now because of that high raw error rate.
Absolutely mandatory. It's not an add-on. It's an integral part of the PCIe 6.0 PHY definition for PAM4 operation. And interestingly, the need for FEC directly led to another major architectural change for PCIe, something called FLIT mode.
FLIT mode. Okay, what's that about?
FLIT stands for Flow Control Unit, and using FLIT mode encoding is mandatory when running at the 64 GT's PAM4 speed. The primary driver for introducing it was the FEC.
Oh.
Well, FEC algorithms work most efficiently and effectively when they operate on fixed-size blocks of data. Variable length packets, like PCIe traditionally used, make FEC implementation much more complicated.
Ah, okay. So FLITs are these fixed-size blocks that the FEC works on. How big are they?
A standard FLIT is 256 bytes. Always. This fixed structure contains payload space for the actual data packets, the TLPs, transaction layer packets, and the DLLPs, data link layer packets, but it also includes dedicated fields within that 256 bytes.
What kind of fields?
There are 8 bytes reserved for a very powerful CRC, a cyclic redundancy check for error detection, and crucially 6 bytes are dedicated to the FEC parity information itself. The FEC calculation covers the TLPD LLP payload and the CRC within the FLIT.
So everything data, error detection, error correction info gets neatly packaged into these 256-byte chunks. How does that affect things like efficiency or latency?
It actually helps bandwidth efficiency, especially for transactions involving lots of small packets. By using fixed FLTs, you get rid of the variable framing overhead associated with traditional packet structures, like star 10 markers, sequence numbers per packet. It simplifies things and packs data more densely.
On latency.
It contributes to more predictable latency because the link processes these uniform blocks. Now, there's some added complexity in the controller logic, obviously, because you have to segment larger TLPs into multiple FLTs and reassemble them at the other end. But the FEC itself is designed to be incredibly low latency.
How low?
The target latency add for the FEC encoding and decoding is less than 2 nanoseconds. It's designed specifically not to impede PCIe's traditional low latency performance.
Wow, less than 2 Ns. That's incredibly fast for error correction.
It's a lightweight FEC designed for a specific purpose. It's meant to clean up the expected errors on a reasonable good, well-trained PAM4 channel. It's not designed to magically make a fundamentally broken channel work. And it uses a technique called three-way interleaving. This is clever because it helps deal with burst errors. Remember, we said PAM4 errors often happen in clumps. Interleaving spreads the bits of a logical code word across multiple FLATs on the wire. So a burst error hitting one spot on the wire is less likely to corrupt too many bits within a single FEC code word, making it easier for the FEC to correct. Each code word can correct a single symbol error, which is 2 bits for PAM4.
So the FEC handles the everyday errors. What happens if it gets overwhelmed or makes a mistake itself?
That's where the second layer of defense comes in, that robust 64-bit CRC within the FLAT. After the receiver gets a FLAT and runs the FEC decoding, it then calculates the CRC on the corrected data. If the CRC check passes, great. The data is considered good. If the CRC check fails, it means the FEC either missed an error or, much less likely, introduced one via miscorrection.
How good is that CRC?
Extremely good. Your sources indicate it can detect up to 8 byte errors within the covered field. The probability of an error getting past both the FEC and the CRC undetected is vanishingly small, something like 2 to the power of a naked 64, essentially 0 for practical purposes.
Okay, so FEC fails, CRC detects it. Then what? Is the data just lost?
No, that's the final backstop, link layer retry. If the CRC fails, the receiver signals an A negative acknowledgement back to the transmitter for that specific FLIT. The transmitter keeps a buffer of recently sent FLITs, the replay buffer, and it simply retransmits the FLIT that failed the CRC check.
Ah, okay. A retransmission. But doesn't that add a lot of latency?
It does add significant latency for that specific FLIT, yes. Which is why the whole system, the channel quality, the equalization, the FEC is designed to make CRC failures, and therefore retries, extremely rare events. The target probability for meeting a retry is down in the 10 error to 10 year range. It's a safety net, not part of normal operation.
Got it. So it's a layered defense. Accept high raw errors. Use super fast, lightweight FEC to fix almost all of them. Use a super strong CRC to catch virtually anything the FEC misses, and only in very rare cases fall back to a retry.
Exactly. It's an intelligent, multi-stage strategy engineered specifically to handle the realities of PAM4 signaling while maintaining PCIe's requirements for both high reliability and low average latency.
Okay, what about equalization? We know PAM4 needs it. Those tiny eyes need all the help they can get. How much did that change for Gen 6?
Dramatically. It was a huge focus. You need really sophisticated equalization to open up those 3 small eyes, enough to meet that 10-IR FBER target before the FEC even gets involved.
So what got upgraded?
Several things. On the receiver side, the analog part, the CTLE continuous time linear equalizer, which provides some initial frequency boost, got more complex. More poles and zeros for finer control over the frequency shaping.
Yeah, analog improvements. What about the digital side? I've heard something with the DFE.
Yes, the DFE, Decision Feedback Equalizer. This is the digital filter on the receiver that cancels out ISI, the interference from symbols that have already been received. For PCIe 6.0, the DFE underwent a massive upgrade. It went from just 3 taps in PCIe 5.0
The 3 taps.
to 16 taps in PCIe 6.0.
16. Wow. That's more than 5 times as many? Why such a huge jump? What do those extra taps let you do?
It's all about tackling long-tail ISI. With the very small vertical eye height of PAM4, even tiny residual amounts of ISI stretching out from symbols that arrived many bit times ago can be enough to cause errors. A 3-tap DFE can only cancel interference from the immediately preceding symbols. A 16-tap DFE can look much further back into the history of the received signal and actively subtract out those lingering echoes and reflections that cause this long-tail ISI. It's absolutely crucial for cleaning up the signal enough to reliably distinguish those 4 PAM4 levels.
So it's like having much better noise cancellation, but specifically for the echoes generated by the channel itself.
That's a good way to think about it. It needs that deep memory to clean up the subtle, lingering distortions that would otherwise kill your signal margin.
And setting all this up, the CTLE, this massive 16-tap DFE, plus the transmitter's own equalization, TXEQ, that must make the link training process incredibly complicated.
It is significantly more complex. Interestingly, for 64 GT's PM4, the link doesn't just start training directly at that speed and mode. It follows the standard PCIe training sequence. First establishing a stable link at lower speeds, then it trains up to a fully equalized 32 GT's NRZ link, basically. It gets to PCIe 5.0 operational speed first.
So it uses the Gen 5 speed as a stable foundation before attempting the PM4 training.
Exactly. It provides a much better calibrated starting point. Then it transitions into the specific phases for training the PM4 equalization parameters. And reflecting the complexity, especially of optimizing that 16-tap DFE across 3 different I thresholds, the time allocated in the standard for these PM4 equalization phases, phases 2 and 3 of link training, was doubled compared to previous generations, up to 48 milliseconds each.
48 milliseconds just for fine-tuning the equalizers. That really highlights the complexity.
It does. It's an intricate, automated negotiation between the transmitter and receiver to find the optimal settings for the transmitter precompensation, the receiver's analog CTLE gain, and all 16 taps of that powerful DFE, trying to maximize the opening of all 3 PM4Is simultaneously.
And the CDR, the clock recovery, has to work hand in glove with all this equalization too, right?
Absolutely. The equalization changes the shape and timing of the signal that the CDR sees. The optimal point to sample the data and the optimal voltage thresholds for the slicers can all shift based on the channel impairments and how the equalizers are configured. They all have to adapt together during training.
Man, it sounds like the chips themselves are doing an incredible amount of work. But the signal doesn't just live on the chip, right? It has to travel across the system.
Yeah.
The board, connectors, maybe cables. That introduces problems too.
Totally critical point. The signal integrity challenge doesn't end at the package pins. It extends across the entire physical path, through the chip package, onto the PCB trace, possibly through via changing layers, across connectors which are notorious for causing reflections, maybe even through internal or external cables. Every single one of those elements degrades the signal further.
And that's where you might need extra help along the path, using things like redrivers or retimers.
Exactly. For longer or more complex paths, the built-in equalization in the main endpoint PHYs might not be enough. Redrivers are essentially analog signal conditioners. Think of them as relatively simple linear equalizers placed strategically along the channel.
What they do?
They provide a signal boost, primarily compensating for frequency-dependent loss, helping to reopen the eye before it gets too degraded. They are generally lower power than retimers and add very little latency, which is good for PCIe. There are specific redrivers designed to handle PM4 signals for PCIe 6.0.
Okay, so redrivers give the signal an analog boost. What about retimers? They sound more involved.
They are much more involved. A retimer is essentially a full PHY chip itself. It receives the degraded incoming signal, performs full clock and data recovery, completely retimes and cleans up the data using its own internal equalization and CDR, and then transmits a fresh, regenerated signal out the other side.
So it fully resets the signal integrity budget, like starting over from scratch.
Pretty much. It completely cleans the slate in terms of jitter and ISI accumulated up to that point. This allows for much longer channel reaches, think connections across large server backplanes, or potentially in active optical or copper cables. PCIe 6.0 retimers are sophisticated devices designed specifically to handle FLIT mode and support things like the L0 by low power state pass-through.
So even though PAM4 helps by lowering the Nyquist frequency compared to NRZ at the same speed, you often still need these external signal conditioners in complex systems to make the link reliable end-to-end.
For many practical system topologies, yes. Achieving the required end-to-end signal integrity budget for 64GT's PM4 across diverse platforms, from compact motherboards to large modular servers, often necessitates the use of redrivers or retimers. It's part of the overall system design.
Okay, let's zoom out again. Looking at the big picture, what were the major system-level trade-offs PCIe essentially accepted by making this move to PM4?
Well, the number one win, the driving force, was performance. Doubling the bandwidth per lane to 64 GTs was essential to keep feeding those hungry processors and accelerators. That was non-negotiable.
Performance first. What about power? We touched on this.
Power is nuanced. Yes, the PM4 PHY silicon itself, with its heavy DSP and FEC, can be more power-hungry in active states than simpler NRZ PHYs. But the comparison should be against a hypothetical 64 GT's NRZ solution, which would likely have needed extremely power-intensive analog front-ends and equalizers. Plus, system-level power management features like L0P in PCIe 6.0 help mitigate idle power. So the overall system power impact compared to the alternative might not be as bad as just looking at the PHY chip in isolation.
And cost. Complex silicon sounds expensive.
It is. Designing, verifying, and fabricating these advanced PM4 PHYs and cutting-edge process nodes is definitely more expensive than previous generations. However, the crucial trade-off here is system cost. By enabling 64 GTs over channels operating at 16 GHz Nyquist, PM4 allowed the continued use of relatively standard, albeit high-performance PCB materials and connector technologies. Making 32 GHz Nyquist NRZ work reliably would likely have required much more exotic, and therefore significantly more expensive, board laminates, specialized connectors, and maybe shorter reach limits.
So higher chip cost, but potentially lower total system cost to achieve that speed.
That's the strategic bet. Shift the cost burden towards the silicon, which follows a predictable cost reduction curve with process scaling, rather than demanding physically challenging and costly performance from the passive channel components.
Okay. Design complexity obviously shot way up for the chip designers. What about latency? PCIe needs to be low latency. How did PM4 impact that?
Latency was a paramount concern. The FEC was specifically designed to be extremely low latency, adding less than 2 nanoseconds. The main potential latency adder is link layer retries, but as we discussed, those are engineered to be exceptionally rare, like 1 in a million or 1 in 10 million FLITs.
So negligible impact on average latency for retries.
And the introduction of FLIT mode, by removing some framing overhead, can actually reduce latency for certain types of traffic, especially small packets. Fundamentally, though, the biggest impact on effective latency for large data transfers is simply that the data gets there twice as fast because the link bandwidth doubled.
Makes sense. And that big worry about the million times worse, raw BCR, the reliability question.
That high raw BER is simply the starting point before the error management system kicks in. The whole point of the layered FEC plus CRC plus retry strategy is to take that noisy, error-prone physical signal and deliver an effective data reliability at the link layer that is as good as, or even better than, previous NRZ generations. Reliability isn't achieved by having a perfect signal anymore. It's achieved by intelligently detecting and correcting the inevitable errors.
So the core takeaway here seems to be that PAM4 itself isn't the whole story. It's PAM4 plus this whole ecosystem of advanced digital processing, FEC, CRC, FLIT mode, massive equalization, all working together.
That's precisely it. It's a system-level solution. The move to PM4 represents a fundamental strategic shift in high-speed signaling design, leveraging the ever-increasing power of digital silicon to overcome the physical limitations encountered when trying to push analog signals faster and faster through imperfect copper channels.
Okay, that covers the jump to 64 GTs. What about looking ahead? Has PCIe 7.0 been defined yet? And does it stick with PM4, or do they have to change again?
Yes, the PCIe 7.0 specification was officially released to members fairly recently, and indeed it continues down the path started by 6.0. It uses PM4 signaling in FLIT mode to achieve the next doubling of speed, 128 gigatransfers per second per lane.
128 GTs. Okay, wait, 128 GTs using PM4? 2 bits per symbol. That means the symbol rate has to double again, right? To 64 gigabaud.
Correct. 64 gigabaud symbol rate.
And the Nyquist frequency is half of that, so 32 gigahertz. All in. 32 gigahertz Nyquist. That's the exact frequency where NRZ hit that insurmountable wall back when we were talking about 64 GT.
It is indeed. PCIe 7.0 is now pushing PAM4 signaling directly into that extremely challenging 32 gigahertz Nyquist frequency regime, the very frequency that was deemed too difficult for reliable NRZ operation at half the data rate.
Wow. So the channel loss and signal integrity problems at 32 gigahertz haven't magically gone away. They're just facing them head on now with PAM4.
Exactly. This means PCIe 7.0 requires even further advancements in equalization, potentially even higher tap count DFEs or more sophisticated algorithms. It demands even better performance from channel materials, connectors, and overall system design to minimize loss and reflections at 32 gigahertz. FEC might need enhancements. And just testing and validating designs at these speeds becomes significantly more complex and costly.
So the physics didn't get easier, just maybe the tools and techniques for fighting it have gotten better thanks to the experience with Gen 6. What kind of R&D is tackling 32 gigahertz PAM4?
A lot of focus is on refining those DSP algorithms for equalization to make them more effective and maybe more power efficient. Reducing the overall power consumption of these incredibly complex transceivers is always a huge priority. Continued innovation in lower-loss PCB materials and improved connector designs that behave well at 32 gigahertz is critical. Techniques to meticulously manage reflections and crosstalk become even more paramount.
What about alternatives? Is anything else on the horizon?
Well, for very long-reach applications, co-packaged optics, CPO, where optical interfaces are integrated very close to the silicon die, is definitely being explored as a potential future path. But for the mainstream, inside the box and chip-to-chip interconnects where PCIe dominates, electrical signaling over copper is expected to continue for the foreseeable future. PCIe 7.0 firmly sticks with electrical PAM4.
So the choice for Gen 7 seems pragmatic. Stick with the known entity of PAM4, leverage the Gen 6 experience, and tackle the known, albeit extreme, challenges of operating at 32 gigahertz Nyquist, rather than jumping to something even more complex like, say, PAM8.
That appears to be the strategy, yes. PAM8 would use 8 levels, giving 3 bits per symbol, which could lower the Nyquist frequency again. But it would come with even smaller I heights, drastically worse SNR, and even higher PHY complexity. Sticking with PAM4 and pushing the frequency seems to have been judged the more practical path forward for 128 GTs.
This has been a really illuminating journey through the signaling shift. We saw how that relentless need for more bandwidth finally pushed the trusty old NRZ signaling past its physical limits for PCIe.
And how the move to PAM4 was this clever strategic pivot, doubling the data rate, crucially, by operating at a Nyquist frequency that was, at least initially for Gen 6, more manageable than where NRZ would have needed to go.
But that PAM4 bandwidth efficiency definitely came at the price of a much noisier signal, lower SNR, way higher raw error rates.
And the real engineering marvel isn't just PAM4 itself, but that whole integrated system built around it. The mandatory super-fast SEC, the incredibly robust CRC acting as a safety net, the efficiency gains of T mode, and especially those massively powerful adaptive equalizers like the 16-tap DFE. They all have to work in concert to pull reliable data out of that inherently messy PAM4 signal.
Yeah, it's a prime example of leveraging the incredible advancements in digital processing power to effectively sidestep the increasingly difficult physics of high-speed analog signaling over copper.
And understanding this fundamental change really helps you appreciate how the data highways inside your own computers are being rebuilt to power the next wave of demanding applications.
It really is wild to think about PCIe 7.0 now tackling 32 gigahertz Nyquist with PAM4, a frequency that seemed like a hard barrier for NRZ just one generation earlier at half the speed. It really makes you wonder, doesn't it? How much further can they push electrical signaling down copper wires? Is there an ultimate limit, and when do we hit it?
Yeah.
And what comes after that?